Hello, I want to talk about the gas laws today in Chapter 7. First of all, I want to tell you that the only difference between a solid, liquid, and a gas is the distance between particles. That's it. Okay, so gases are the farthest apart, then liquids, then solids. So if particles come close enough together, they will become a liquid and then they will become a solid. It is that simple. That is the only difference between a solid, liquid, and a gas. That's what makes them what they are. So because gas particles are so far apart, they will collide with the sides of they're free to move around, and they will collide with the sides of their container. And when they do that, they create pressure. Pressure equals collisions, collisions equal pressure. So very, very simply, if you increase the number of collisions, you will increase the pressure of the gas. Now, clearly, it needs to be a closed container, okay? Because if you increase the collisions, they'll move farther apart and they'll escape out of the container. So the ways to increase collisions are to increase the temperature or to move them closer together. Or you can decrease, another way is decrease the volume, okay? So if you decrease the volume, all of a sudden the particles are a little closer together, and that means they're colliding with the sides of the container more and more. So that's really all you need to know about gases. Everything else kind of falls into line when you understand that. And we call that the kinetic molecular theory. So make sure you look through that, because that is your cheat sheet. The kinetic molecular theory will tell you everything you need to know about gases. So very briefly, let's just talk about a couple of the gas laws, and you can see how this works. So Boyle's law is about pressure and volume. So let's just think about that. Let's say you have a container of these particles, okay? And you decide to, now some of them are hitting, they're colliding, and then you increase the pressure on that system. And now you still have the same number of particles, but as you can imagine, they are going to hit off the sides of that container, and they are going to have more collisions. And remember, I already said, more collisions means more pressure. So if you increase the pressure, you decrease the volume, okay? And so that's an inverse relationship. So if you know pressure 1 and volume 1, you can get pressure 2 and volume 2. Now, these can be any units of pressure, but they must match up on both sides, okay? After you understand the kinetic molecular theory and how this works, the rest of the gas laws kind of fall into line. I do want to talk about Charles' law briefly because that's volume and temperature. So let's just say that you keep the pressure constant and you've got this container of gases, and you decide to heat it up, okay? Now, what's going to happen is as you heat up particles, they are going to start vibrating more and more. And that's what heat is. It's particles vibrating more. And as they vibrate more, they move more, and they're going to collide with the sides of the container. And if you're trying to keep the pressure the same on the outside of that container, and especially a balloon is a really good way to do this, then the volume would have to increase. So as you increase temperature, the volume would have to increase so that you can keep the pressure constant. And so we call that Charles' law. So as volume goes up, temperature goes up. So V1 divided by T1 would give you the second volume over the second temperature. So as long as you know 3 of those, you can get the 4th number. Now, what I want to talk about here is this temperature thing. You must use absolute temperatures. In other words, you must, with all of the problems in Chapter 7, you must use the Kelvin temperature scale. Because if you use the Celsius temperature scale, you will get some negative pressures and negative volumes. And you can't have that. That's bad, okay? So you gotta make sure with all of them that you use the Kelvin temperature scale. You should be able to derive Gay-Lussac's law and the combined gas law quite easily from both of those, the same manner that I just did. I do want to talk about Dalton's law briefly. Now, the beauty of Dalton's law is that you can add pressures of different gases together to get the total pressure. And that's because pressure depends only on the number of particles, not what they are, not the identity of those particles. So in our atmosphere, for instance, if you want to know atmospheric pressure, you would add all of the pressure of the nitrogen, you would add all the pressure of the oxygen, you would add all, they all, on and on and on and on, they all exhibit their own number of collisions, and you can just simply total them up if you know their individual pressures. In other words, if you took the nitrogen out of the air and you put it in its own little container, it would exhibit its own little pressure against the sides, okay? Same thing with oxygen, etc., carbon dioxide, argon, all of the gases in our atmosphere. They all exhibit their own little pressure. So in a mixture, it doesn't matter what the gases are. All that matters is the number of particles. We have a really cool law. It's kind of a shortcut from the ideal gas law. Ideal gas law, and by the way, ideal gases don't exist. We just use this because it cuts down on the amount of math that we have to do. So if you take upper level chemistry, and who wants to do that, you can have a mathematical correction for this law. But we just keep it simple in lower level chemistries. And you're not in low level, it's just that it's people that aren't going to be a chemistry major, they don't need to know the mathematical corrections. But the ideal gas law says that pressure times volume equals the number of moles times a constant times the temperature in Kelvin. Now, if you have standard temperature and pressure, okay, pressure, temperature, you can rearrange this equation to say that at STP, 1 mole of any gas. Remember, it doesn't matter what the gas is. All that matters is how many particles. And 1 mole, remember, is 6.02 times 10 to the 23rd particles of any substance. And when you do that, you will come up with 22.4 liters. If you change the temperature, if you change the pressure, then you're going to need to use the ideal gas law to find the volume. But at standard pressure and standard temperature, you can use this for a nice little shortcut. All right, I hope that helps. And I will post another video on specific heat and the heating curve.